Today we will be talking about basic electricity, and in the next few days we will be learning about electric circuits. Please follow along and fill in the blanks in your notes handouts. Remember, anything you miss can be found on Edmodo. Before we can understand how an electric circuit works, we need to understand what electricity is. We spent the last few weeks learning how electric charges behave when they're staying still, i.e. electrostatics. But what about when they start to move? The collection or flow of electrons in the form of an electric charge is known as electricity or electric current. Electricity can be symbolic of fluids. Circuits are very similar to water flowing through a pipe. A pump basically works with two important principles concerning its flow. There is a pressure difference where the flow begins and ends, and a certain amount of flow passes each second. A circuit basically works on two important principles. There is a potential difference, or voltage, from where the charge begins to where it ends. The amount of charge that flows per second is called current. We can think of this like the oil pipelines located around Odessa. The pumps pump the oil through the pipelines and send it to somewhere else. They rely on pressure, or pounds per square inch, to push the oil through the pipeline. They gauge how much oil is being sent by how much passes in a certain amount of time, or second. Gas pumps work the same way. That's how they know how much money to charge you, is based on how long you've been pumping and how much has flowed through those pipes. Let's briefly review potential difference. In a battery, a series of chemical reactions occur in which electrons are transferred from one terminal to another. There is a potential difference, or voltage, between these two poles. The maximum potential difference a power source can have is called the electromotive force, or EMF. We're going to use an E to symbolize this. Okay, this term isn't actually a force. It's simply the amount of energy per unit charge, which is joules per coulomb, or a volt. Current is defined as the rate at which charge flows through a surface. The symbol that we're going to use for current is I. I know it seems logical we should use a C, but we've used C for so many things already, we're running out of letters, so we're going to go with I. So our equation is going to say I equals Q divided by T. Remember, Q stands for charge, and T stands for time. That gives us a unit of coulombs per second. We're going to also call that an ampere, which is often shortened to amps, and the symbol for this unit is going to be a capital A. The current is always the same direction as the flow of positive charges. That means it's opposite the direction an electron would move, because an electron is negative. There are two types of current. The first type is DC, or direct current, which means current flows in only one direction. The best example of this is a battery. Okay, so if we look at our circuit we have here on the side, the current starts at the negative end of the battery, goes around through the light bulb, and back to the positive end of the battery. Remember, the direction of the current is opposite the direction of the electrons. If we were to graph current compared to time for direct current, we would get a constant, which means our graph would look like a straight line. Our second type of current is AC, which is alternating current. This means the current reverses direction many times per second. This suggests that AC devices turn off and on. An example of this is a wall outlet. This is helpful because when we are not using the electricity, it's not flowing, and that keeps our electric bill lower. Because batteries are direct current, that's why they have a shelf life. So even if you're not using them, they can still go dead. So if we were to graph current versus time for alternating current, we're going to get what looks like a sine wave. A basic circuit must have three main parts. First, we need a source of energy. If we don't have energy, it's not going to work. Next, we must have a closed path. And third, we need a device that's going to use the energy. Something such as a light bulb, a computer screen, something that's going to get hot, anything that can use the energy. If any part of the circuit is open, the device will not work, i.e. there is no current flowing through that circuit. Please take a few seconds, copy down these two drawings of electric circuits, and see if you can identify which one is open and which one is closed. Alright, let's see if you got the correct answer. The electric circuit on the right is considered to be our closed circuit. If we trace this all around, we can draw the whole thing without lifting our pencil, which means our electricity can get through all of this without getting lost. But the one on the left is considered to be open. You see, we have a giant hole here in the corner. Open circuits are very bad. This means we have extra electrical charges flowing out somewhere, and this is how people get zapped. You can think of this as like a broken light bulb, but you still have the light switch turned on. There's still electricity flowing, but it has nowhere to go. That's an open circuit and very dangerous. If we go back to our oil pipeline analogy, we can think of the open circuit as a broken pipeline. Somewhere there's a hole in it and oil is getting out of that pipeline because it's open. Let's try a few sample problems. Sample problem 1. How long does it take a current of 5 milliamps to deliver 15 coulombs of charge? Okay. Our givens for this problem are 5 milliamps. Remember, anytime we have an SI prefix, we must convert to the base unit. Milli equals 10 to the negative third. So this is equal to 5 times 10 to the negative third amps. Our other given information is 15 coulombs. There is no SI unit prefix in front of this, so we do not need to convert. Our unknown for this problem, the question says, how long does it take? How long is a reference to time. So for unknown, we're going to write t equals a question mark. We know that the equation for current is current, remember we use I for current, equals charge divided by time. But something's missing. I have this equation here, but how do I know which number goes in which spot? What we need to do is we need to look at our units, and based on our units, determine which quantities these given numbers belong to. If we have amperes, that is the unit for current. So this 5 times 10 to the negative 3 amps must equal I in our equation. And we know coulombs is the unit of charge. 1, because we've memorized that, and 2, it tells us 15 coulombs of charge in the problem. So 15C must equal Q from our equation. Okay, now we need to solve our equation. We can do this one of two ways. The first way is we can rearrange our equation first. We have I equals Q divided by T. We know we're solving for T. In order, right now T is on the bottom of the fraction, which doesn't work very well for us. So let's try and eliminate the fraction. If we multiply both sides by T, we get T times I equals Q. Then in order to get T by itself, we must divide by I. So T equals Q divided by I. We can also use the triangle method. Q is on top of our fraction, so Q goes in the top of the triangle. And then we have I and T on the bottom. Remember, the middle line means to divide, and the vertical line means to multiply. So now, let's substitute in our numbers. We have T equals 15 divided by 5 times 10 to the negative third. When we simplify this, we get time equals 3 times 10 to the negative third seconds. And in your calculator, it may look like 0.003 seconds. If we had tried to plug in the numbers and then solve, we should have gotten the same result. On to sample problem number 2. This problem says if there is a current of 10 amperes in a circuit for 10 minutes, what quantity of electric charge flows through the circuit? Okay. So, our given information is 10 amperes, and that says of current, so that must equal I. That's already in our standard unit, so we don't need to convert. But then it also says 10 minutes for time. Minutes is not our standard unit, and we need to convert to seconds. We know that 1 minute equals 60 seconds. If we start in minutes and need to go to seconds, we need to multiply 10 minutes times 60 seconds. Therefore, we get time is equal to 600 seconds. The unknown in this problem is charge. So we're going to write Q equals a question mark. Just like our previous sample problem, we're going to use current equals charge divided by time. Our next step in the problem is to substitute. This time, let's try substituting in the numbers before we rearrange the equation. Based on the given information that we wrote down, we now have 10 amperes for our current is equal to the charge divided by 600 seconds for our time, because we had to convert. To solve this equation, the first thing we have to do is multiply both sides by 600 to get rid of our fraction. 600 times 10 equals 6,000 coulombs of charge. On to sample problem number 3. This question says, how much current must be in a circuit if 100 coulombs flow past a point in the circuit in 4 seconds? Our given information for this problem says 100 coulombs. We know coulombs is how we measure charge, so that's equal to Q. It doesn't say anything about an SI prefix, so there's nothing we need to convert. And then it says 4 seconds, and we know seconds is our standard unit for time, so that must equal T. The question asks us how much current, and current is symbolized with a capital I, and that's our unknown, so it equals a question mark. Just like the last two problems before, we're going to use the equation I equals Q divided by T. Alright, the next step in our problem is to substitute. So we get I equals 100 coulombs divided by 4 seconds. And when we solve that, we get I equals 25 amps, or amperes. Now, our last sample problem for the day. Problem says, if there is a current of 2 amperes through a hairdryer transferring 15 kilojoules of energy in 55 seconds, what is the potential difference across the dryer, and what is the charge of the hairdryer? Our given information says that current is 2 amperes, time is 55 seconds, and the energy is 15 kilojoules. That number is the only one in the given information that has an SI prefix, so that's the only one we need to convert. We know kilo is 10 to the third, so that if we convert that by multiplying, we get 1.5 times 10 to the third, fourth, because we had a 2-digit number before, so we need to add that to our exponent. So 3 plus the additional 1 gives us 4 joules. We have 2 unknowns in this problem, so we're going to color code them. In blue, we're going to solve for the potential difference. Remember, potential difference and voltage are the same thing. So, voltage equals a question mark. Our second unknown is charge. We know charge is symbolized with a Q. Okay. To solve the first part of this problem, we have to go back to the notes that we learned about last week. We learned that the voltage is equal to the change in energy divided by the charge. Charge and voltage are both our unknowns. So even though the question asks us for the potential difference first, we actually have to solve for the charge first. And to do that, we're going to use current equals charge divided by time. Now let's substitute in our numbers into the current equation first. We get that current of 2 amps equals charge divided by 55 seconds. This time, let's solve this equation using the triangle method. We have Q on top, and then 2 and 55 on the bottom. Using the triangle method, this tells us we need to multiply 2 and 55. So we get a charge of 110 coulombs. Now, using that answer, we're going to plug our given information into our second equation, the voltage equation, which is the one written in blue. And we get that voltage, which is also called potential difference, is equal to 1.5 times 10 to the 4th divided by 110 coulombs. As we enter this into the calculator, remember that times 10 is also the same thing as EE. In the classroom calculators that I provide you, the EE button is directly above the 7. So after we enter this all into the calculator and solve, we get an answer of 136.4 volts. That's all for today. Remember, if there's anything you missed or don't understand or would like to watch for any other reason, this video is posted on Edmodo. This video is also posted on YouTube, so if for some reason you can't find it on Edmodo, you can just search Rebecca Orcutt on YouTube and find my YouTube page with all of our class notes on it.